Hey everybody. Today we're talking about the chi-square distribution. This is a continuous distribution that measures how far a set of observations are from their expected values, sort of overall. The idea is you take each of your observations, say we have R of them, you compute their z-scores, square those, that makes them all positive, and then add them all up. And the idea here is that the result is going to be 0 only when all of those observations are exactly at their expected values. And the result, chi-squared, is going to get larger as you have more departure from those expected values. Since each of the individual z-scores is a continuous random variable, so is chi-squared, when each of those observations is coming from a normal distribution, so those z's are actually z-scores in a standard normal distribution, then the sampling distribution of the random variable chi-squared is said to have a chi-squared distribution with r degrees of freedom, or chi-squared of r for short. Notice that we are using chi-squared in two different senses here. The distribution chi-squared of r and the random variable chi-squared. The context pretty much always makes it clear which one we're talking about, but it is something to be aware of. The chi-square distribution comes up frequently in inferential statistics. A few of the most common places where you'll run into it: goodness of fit testing for a single categorical variable, significance testing for variance, confidence intervals too for that matter, testing the independence of categorical variables. The probability density function for chi-squared of r is always skewed to the right, and its support is always only the positive real numbers. Here's a graph of chi-squared of 5, which is totally typical. You can see the long right tail. The expected value of chi-squared of r is always r. So here I'm showing chi-squared of 5 with its expected value to the right of the mode of that distribution. And I think that makes sense since the chi-squared random variable is defined to be the sum of r z-scores squared. And we know that the standard normal distribution has mean 0 and standard deviation of 1, so it makes sense that if you square that, the expected value of each one of those squared z-scores would be 1. When r is large, the distribution chi-squared of r is approximately normal. And that's a consequence of the central limit theorem, although I won't go into the details here. And you can already see that normality with r equals 50 that I have pictured here. But if you squint or just look a little bit closely, you can still see the skew in the plot. The tail is fatter on the right. The mean is not at 50 as you would need if this was in fact exactly a normal distribution. As with any continuous random variable, we compute probabilities in the chi-squared distribution using the cumulative distribution function, or CDF. And that represents the probability of randomly getting an observation less than or equal to a specified value in that distribution. You should always do that using technology, although tables do exist for these chi-squared distributions. I use R where the command is p chi-squared. So, for instance, to get the probability that you randomly observe a chi-squared value less than or equal to 10 in chi-squared of 8, that is to say the chi-squared distribution with 8 degrees of freedom, we do p chi-squared of 10, 8, and we get about 0.725. Let's wrap up with a couple more examples. And if you want, you can pause the video and try and do these on your own before seeing my solutions. First off, let's compute the probability that chi-squared is greater than 8 in chi-squared of 11. So I have displayed that probability here as an area. We're looking at the area under chi-squared of 11 to the right of 8. We're going to do this by finding the area to the left of 8 and then subtracting that area from 1. In other words, using the rule of complements. I'm doing 1 minus the probability that chi-squared is less than or equal to 8, 1 minus p chi-squared of 8, 11. I get about 0.713. By the way, I can be sloppy with the senses of my inequalities here. I don't have to worry about greater than versus greater than or equal to, less than versus less than or equal to, less than or equal to. And the reason is that I'm talking about a continuous random variable, so the probability of an individual outcome, like chi-squared equals 8, is essentially 0. One more example. Compute the probability that chi-squared is between 10 and 12 in chi-squared of 11. Here's the picture. I'm going to find the area to the left of 12 and then subtract off the area to the left of 10 to get the area in between 10 and 12. p chi-squared of 12 comma 11 minus p chi-squared of 10 comma 11, I get about 0.167.